Hi, Algebra 2. Here we are. We're in section 12.2, and we're looking at permutations and combinations. So if you ever considered choosing out of a group of things, let's say we had this group of beautiful dresses that we were trying to figure out how to choose, how many choices we have in choosing. So let's say I have these 9 dresses and I want to choose 3. If I want to choose 3, what's the probability of me choosing, or I keep saying probability, we'll get to that later. Sorry about that, guys. How many different ways can I choose 3 different different combinations? I just want 3 different combinations, not necessarily that 3, but just any 3 different combinations of dresses. How many different ways? That question is answered by combination. You just want to know how many different ways can you choose 3 things. But permutation is going to be like this. How many different ways can I choose 3 things and order them in rank of first, second, or third, right? So in that case, let's say I chose shirts or dresses A, B, C, but that's only one way of organizing that. I have to also keep thinking about, for every group of 3, basically, I have to think about the fact that I can organize them in 6 different ways. So it could be ABC. So let's just write it down. It could be ABC, ACB, BAC, BCA, CAB, and CBA. And that's just for these 3. That's how many different choices I have in a permutation. Because a permutation considers the order. So it considers the order, or the placement. Placement is important here. So I'm going to use the kind of alliteration here, not alliteration, but you know what I mean. I'm just going to use the mnemonic device to say P permutation means placement, and you'll often see that order does matter. So it's not just about how many different ways I can choose 3, it's how many different ways I can choose 3 and how many different orders they can be. So for each 3, whether it's this 3 or you know what I mean, we can do that. But with combinations, it's just how many different groups of 3 I can find. So it's just choosing is what's happening here. You're just choosing 3, no order, and order doesn't matter. Order does not matter. Okay. So the next concept that we're going to talk about is the linear permutation. And the linear permutation is really just the different ways that people or things can be lined up. So it's, again, dealing with order, the different organization of a line of things, people, items, jewelry, fruit. All right, with that, let's get started. So when you're dealing with a permutation, remember, this is when order matters. This is how you will calculate all of the distinct possibilities. So the number of permutations of n distinct objects taken R at a time. The last problem we had was P. We were dealing with, if you go back real quick, 9 shirts and we were choosing 3. That would be 9 objects chosen 3 at a time, right? So the permutation of n distinct objects taken R at a time, it would be the whole number of things and then the number I'm choosing. And this is what you would do. You would say, okay, well, n factorial, that's the whole thing, divided by n minus R factorial. So that would be subtracting out, basically in this case would be 6 factorial, 9 minus 3 factorial, which comes out to 9 factorial over 6 factorial. So that would be the value. And this totally kind of makes sense if you think about it in terms of just choosing place values for each of these 3 things, right? Because I'm looking for 3 different shirts. I know, I'm so tired of this example too, don't worry. So out of 9, so the first one I have 9, the second one I have 8 choices, and the last one I have 7 choices, right? And that would be, that includes all of the different orders. So that's going to count all the different orders. Why is this important? It's important to know because I think you can go back and kind of process a little bit. So watch this. 9 factorial we know is 9 times 8 times 7 times 6 and so forth and so on. I should get a 4 in here, 3, 2, and 1. And then 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1, 1, And then you can see if we cancel those out, we're left with what we kind of expected to have. So that's what a permutation is. Order matters, and we would use this. Oh, by the way, sometimes you might see it in other textbooks like this. So you could see it like that. You could see it like this, as our textbook is using, and we know it means this. All right, let's go ahead and see if we can do an example. Here in example 1, we're dealing with a permutation because there are 10 finalists in a figure skating competition. How many ways can gold, silver, and bronze medals be awarded? So we have these, silver has an R. So we have these different categories. We want to choose 3 out of the 10. And so I know I'm bringing home this point too much, but choosing 1, 2, and 3 is different from choosing 3, 2, and 1, even though we're talking about the same people. So I want you to keep that in mind. So what did we learn in the last situation, or the last slide? We learned that the permutation is going to be, in this case, 10, choose 3. And we know we can write it like this: 10, choose 3. We're looking for that permutation, and that's going to be 10 factorial over 10 minus 3 factorial in the denominator. And it kind of works out to be the same thing, right? You know, you've got 10 choices for gold, then 9 for silver, and then if we look at it this way, then maybe 8 for bronze. So we should expect to see that here, and we do, because 10 factorial divided by 7 factorial leaves 9 times 8 times 10, which is going to be 720. So there's 720 different ways that we could have the 3 finalists take gold, silver, and bronze. So here's another bit of information we should hold on to. So this requires us to think about permutations with repetitions. So if we were talking about organizing things that have the same, like if I'm thinking about or how many different ways can I rewrite the word, I don't know, beat. All right, so beat has 2 E's, so that's going to change the number of unique different things that we can get. So in this case, we're finding out how to handle that. So the number of permutations of n objects of which P and Q are alike would be done like this. So we would take n factorial divided by P factorial divided by Q factorial. So I probably should not have erased the word beat, but if we think about the word beat, we know that we have n numbers, and so that's 4 factorial, and we only have one thing that's being repeated twice, so here we have that. I'm going to write 2 factorial because we see it's twice there, and so the number of different ways we can organize this would be 4 factorial is 24, and 2 factorial is 2, so there's 12 different ways we can organize the letters in the word beat to make distinct different letter organization choices. Okay, hopefully that makes sense. So in this example, we're going to apply that. So how many different ways can the letters of the word Mississippi be arranged? And so we know that it's going to be first thing we need to do is figure out how many letters we're dealing with, and in general we have 11 letters in this word, so that's 11 factorial, and we're going to divide out by the factorial of how many copies there are. So I'm looking at I, and I see that there are 1, 2, 3, 4 I's, so I'm going to write 4 factorial down here because there's 4 different arrangements of those I's that would keep getting counted. And then I can do the same thing with the S's. There's 4 of those. So I would put 4 factorial, divide out by 4 factorial. So I'm dividing out all those repetitive things where those S's are mixed up, but it doesn't make for a distinct, different set of letters. And then finally, I'm going to highlight the P's because there's 2 of those, and 2 factorial will take care of that. And so when we plug it into our calculator, because it's a lot, we would get that there are 34,650 different ways to arrange these letters distinctly. Okay? So in this situation, we're going to take into thought combinations. Remember, combinations, order doesn't matter. So since order doesn't matter, we're actually going to have less less choices. And if you think about it, remember when we were doing the other example, this one here with the figure skaters and they're, being awarded points, and I was like 1 2 3 and 3 2 1, and I could have gone on with 6 different things, are all exactly the same. They are all the same values, but they're all the same, like winners, 2 3 1, whatever. They all represent the same winners, but they don't represent the same, order. Well, in combinations, when we are choosing some values, we have to divide out the possibility of all those extra replications of the same group taken, but in a different order. So that's why order doesn't matter, actually produces less choices. So let me get into it. So this is N choose R, and I think we've used this language before when we were looking at binomial expansion theorem last chapter. What we have here is a combination of N choose R. So I don't know. Let's go back to the shirts that I was choosing in the very beginning. We had 9 shirts or 9 dresses, and we were choosing 3. And what happens here? This looks a lot like a permutation, right? Permutation is the N value divided by N minus R. So in this case, N minus R is 6 factorial. But then we have to take into account those copies. So then we do 3 factorial. You've seen me do it a number of times. You know that 3 factorial is 6. So I'm dividing out 6 because for each of the different combinations, there's 6. Y'all with me? All right. So let's check on an example. So here's an example of combinations. A group of 7 students working on a project needs to choose 2 from their group to present the group's report to the class. How many different ways can they choose these 2 students? So we've got 7, choose 2. We remember what this looks like. It is 7 factorial over 7 minus 2 factorial. And now I got to get rid of the copies, 2 factorial, where like that would have been if I cared about order. So now I will calculate this. I could put it in a calculator, but I know 7 factorial divided by 5 factorial is going to leave me with just 7 times 6. You guys can picture that, over 2 factorial. So 2 factorial is just 2. 7 times 6 is 42. So I know that there's 21 ways that that group can choose those 2 students who are going to present to the class. So in this problem, example 4, this is going to be multiple events. So we're going to be looking at it in terms of like the fundamental counting theorem that we talked about last time. 5 cards are drawn from a deck of cards. How many hands consist of 3 clubs and 2 diamonds? So what we need to think about is how many clubs are there and how many diamonds are there in a deck of cards. And if you're not familiar with a deck of cards, I will tell you. There are 13 clubs and there are 13 diamonds. There's 13 of all 4 suits. And so now what we need to do is consider how can we choose, how many different ways we can choose these 3 clubs and how many different ways we can choose these 2 diamonds. And so that would be this situation, right, for the clubs, and then this situation for the diamonds. But the thing here is we want to know all the possible ways that can happen. So we're going to actually end up multiplying those guys together. So it won't be just 13 choose 3 and 13 choose 2. It'll be 13 choose 3 times 13 choose 2. All right, let's get started. So that's 13 factorial over 13 minus 3 factorial, which is 10 factorial, over just 3 factorial. And I'm going to multiply that by 13 factorial over 13 minus 2 factorial, which is 11 factorial, divided by 2 factorial. I think I should probably get my calculator out, but I'm going to be stubborn just for a little while. 13 times, no, I'll get my calculator. So we'll get 286 times 78, with its product being 22,308. And so that's how many different ways that we can draw 5 cards from a standard deck and find that we have 3 clubs and 2 diamonds. I know you wanted to use the 5 in that equation, so did I. But this makes sense when you realize we're just counting how many possible situations we could have in this way. What are the different ways that we can get this? Okay, with that in mind, I look forward to talking to you guys soon. As you know, let me know if you have any questions. And if not, then I'll see you next week. Take care.